there was 5 problems, so it shouldn't go above 7. I mean, the what's the name of it? The tutorial had 20 problems, so naturally that was a one-time thing. Okay. Okay. So any questions about improper integrals? Okay, so we are expanding of the idea of Riemann integral, and especially the Riemann integral as the area under the graph of a function to a case that wasn't used to be covered, okay, by the in calculus 1, and that is infinite regions, and infinite regions are carefully to be understood as. So this is an infinite region, certainly, but these not all infinite regions look like this. So what we have considered so far only were infinite regions with infinite width or infinite domain, and so that is totally visible in the integral, because you suddenly see something that you didn't used to see, and that is the infinity as a limit. Okay, so that's what you see. But that's only one class of improper integrals, and the other one is the ones that are not infinitely wide, but rather the ones infinitely tall. We already saw a little bit of that with the 1x. So remember this one. So an infinitely tall region. So we still want to be able to cover these as well. They do not fall into the category of infinitely, so they don't fall into what we have already considered. Okay, so if this is 1 over x, y equal 1 over x, so as you can see, the region lies entirely under the graph, but it continues on indefinitely into infinity along the y-axis. So it used to be along the x-axis, so in fact it's still the case with 1 over x. There is an infinite region to the right, and now we're looking at the infinite to the left, and we also want to handle it, and we know how. It's really not a challenge anymore, because we know how. The idea is to exhaust the infinite region with finite regions, and then take the limit. Okay, so once again, this is the something like this we can always handle if the two limits are finite, the function is finite. Then we're good, and then we can vary the two limits, or one rather, one at a time, in order to handle infinite regions. Okay, so in this particular case, it's exactly the same, but it is not really that different from the case we started, because it was if it was original integral from 0 to infinity. Okay, and once again, remember, infinity is not a number, so that's why. The original definition of the Riemann integral does not apply, because the graph continues on to infinity, and then it is at infinity. There is nothing at infinity. Similar thing happens here. The graph is the function is defined all over the place here. Okay, so this one is included. Let's say b, but there is a hole in the domain. Okay, a hole. So this. 0 is missing. The 0 is missing, just as infinity was missing from the domain. So we want to have an infinite region, and then one value is missing. And the same thing story is here. 0 is missing, so we cannot think of what we see here in this manner. Okay, that's the only manner we're able to handle it with calculus 1 tools only. Fortunately, we know how to do it. We cut it we fix the upper limit, and we let the lower limit progress from left to right. Okay, so this is A. A will be variable, B will be fixed. How about 1? And then we allow the A slide towards the origin, and it'll take the limit. Okay, so let me write the definition right away. The definition is, as before, suppose f is defined on an open Hold on a second. I wanna have a nice letter choice of notation. Okay, so how about I put a, let's see here. Okay, so no, this is A, this is C. Okay, so F is defined an interval which is now not closed anymore, not closed and bounded, but not the calculus 1 is closed and bounded. So for the 2 days we were considering intervals that were closed but were not bounded. Now we're looking at those that are bounded but not closed. So this is the interval that is bounded but not closed. Right. Bounded, not closed. So as you can see, C is removed from the interval. This is C, and this is B. B is included. C is not. The interval is not unbounded. It's not infinite, and yet the trouble with we are facing the same trouble with interval that produces functions undefined. Doesn't have to be defined at the origin, and that's what creates the possibility, only a possibility of the function going up vertically. In fact, we know what we're usually talking about. That's vertical asymptote. So that's the typical situation we are facing. Vertical asymptote. The interval is the graph, or rather the region on the graph expanding to infinity vertically, and then we just want to be able to handle it and compute what that potentially infinite but potentially finite area is. So F is defined, and as before, we assume that it is integrable on AB closed interval whenever A is larger than C, but less than B. Okay, so then now we're looking at this integral, which looks, by the way, entirely innocent. This integral that we're talking about, integral from C to B. C and B are numbers, so as far as we're concerned, we're looking at, if you look at it without understanding what the kind of function this is, you might think this is the regular integral, because both of these are numbers. There is no infinity, no indication that there's any kind of problem, unless you look carefully at the function f, and that's what the preamble of this definition is. It says that f is not necessarily defined at C. Okay, so and then the plan is once again to reduce, get away from C is a little. So I pick A larger than C, and I look at the interval where A is larger than C, so which means that the function is defined, and that this interval as well as it is integrable. So this makes sense. It is a small region, and we are staying away from the problematic point of C, and so this is computable. And then finally, we are just take the limit with A going towards C from the right. Remember this notation? C plus means that A approaching C from the right. So it's A remains larger than C. We don't want to expand to beyond C. Okay, so and then once again, if exists. Okay, so let's look at the example of 1 over x once again. So f of x is 1 over x, and the interval is 0, 1. Okay, so 1 over x is undefined at 0, so we are interested in this area, this infinite area over here. And so the plan is right here. It is a computation that is fairly straightforward. So I take my limit. I take my integral from 0 to 1 over x dx. So that's what I need to find. How? I look carefully. So suppose what in the future might happen. You are looking at the integral that looks totally innocent. So what do? You have to verify that before you do kind of calculus 1 thing, you verify that the function is defined at the endpoints as well and everywhere in between on the whole interval. It has to be defined on the whole interval 0, 1 in order for you to be able to continue and do not worry about the integral being improper. This one is we identify it as improper, so that's the first part of the analysis. So it's improper y, 1 over x, undefined at x equals 0. So if it is improper, then the only way to handle those is through limits, and with this definition right above tells you how. So we take the limit with b approaching 0 from the right, and we have integral from b to, from, this is an a, from a to 1 over x dx, okay? Now, if we said that this integral, the whole integral over here, is improper, okay, this time we say this is proper in the sense that the integral is bounded and closed, so we are in a safe space. We can just integrate it as we always have. So we continue on, and we have our limit. B goes to 0, a goes to 0 plus, and 1 over x gives me logarithm, right? So it will be logarithm of 1, again, minus logarithm of a, which is positive, okay? And then what's the conclusion? Now, so that is the integration is finished. What I have in parentheses there is the answer of my integration. It is dependent on a because the lower end of the integral of the interval was a variable. So okay, so that's why I ended up with a limit, not just a number. It is a function, in fact, where that's what it is. And then I take the limit. So what's the limit? It is infinite. In fact, we can say it is actually positive infinity. Right. Okay. So well, then that's the answer. The area that we're looking at has infinite and positive area. So as you can see, it certainly can happen. Now that's the whole thing. The whole solution is right here. Just like the way we did it with integrals on infinite domain. The domain is finite here, just not bounded, not closed. Remember how we picked, we went from 1 over x, we went to 1 over x squared, and we ended up with an integral that was finite, right? So let's try to do the same from 0 to 1. So the function that looks similar to this, but what would make it finite possibly? It would have to be narrowing down towards the top faster, right? Narrowing down faster. So how do we make it narrow down faster? So if this is 1 over x and this is large, and we want to make it narrow down faster, so it would have to do what? What kind of function is that? What I'm talking about is what is the power? Can you choose the power different from 1 over x? So it should be larger or smaller? Larger power. Well, 1 over x squared, well, let me quickly write it out. So what's the power is, by the power formula, what do I get here? One over x squared, what's the integral? We did it yesterday. The power goes up. What? Negative 1 over x, right? Negative 1 over x plus negative. Yeah. So this will be 1 over a, right? Like this. Okay, so what's the limit? What?
It's 1.
No. What? A goes to 0, 1 away goes to infinity. Okay, so unfortunately, we picked the wrong one. We went in the wrong direction, unfortunately. Well, it happens. So what's the right answer? Let's pick.
1 over x to the half power?
That's right. 1x, 1x r squared if you prefer. So works out exactly the same way. The power still goes up, but 1/2, negative 1/2 goes up by 1, gives me what? One half power goes up by 1. What's the power?
3x.
No, it is negative 1/2, right? This is x negative 1/2, right? So it goes up by 1. It will be x 1/2.
Yeah.
So it will be a 1/2 minus 1. The limit. Hold on a second. It's minus plus. Okay, so the limit is so a goes to 0. Where does its square root go?
So it'd just be 1.
It will be 1, right? So this goes to 0. This one went to infinity, and that was the problem. But this one goes to 1, so the answer is 1. So the area could be finite, but it is the exact opposite situation from that infinite to the right function, and it does make sense. It does make sense. So you just look at the symmetry, which is not symmetric exactly. So 1OX is symmetric, right? 1OX is symmetric with respect to the diagonal. So this is infinite and that is infinite. Okay, so these two are both infinite. However, it is the opposite for, say, 1OX squared. It is actually thicker here and thinner there. So this is y equal 1OX squared. It goes towards 0 faster to the right, but actually it is at close to 0. It actually declines not as fast. So then this part is less than infinity, but this part is infinite. Okay, and similarly, so that's the previous example, and the last example gives me 1 over square root of x, which looks exactly the same, but it is thin here and thick there, like that. So it still goes to infinity. You still have a 1 vertical asymptote, 1 horizontal, but we did this last time, right? We discovered that that infinite strip to the right has infinite area, but this one is less than infinity. It is finite. Okay, so once again, why? Because 1OX squared is not symmetric about. In fact, what is the meaning of the symmetry? Remember the meaning of the symmetry about y equal x. Where does it come from? So if I have a function like this maybe, and then I take symmetry about the, what's the relation between these two functions? The inverse, that's right, inverse. So if this is f, then you take its graph, and it gives you its inverse, right? So the good thing is y equal 1OX. What's the inverse? X is equal to 1 over y, right? So it's inverse of itself, pretty much. So that's why when you flip it, you do the reflection of the graph, and you get the same graph. Okay, so that's what on the right half, and that's why you have two infinities. However, if I take 1OX squared, so how do I find the inverse? I solve for x. So x is equal to what? Y equal 1OX squared. I solve for x. What do I get? Square root. So these two graphs are actually symmetric of each other. And as you can see, symmetric with respect to the diagonal once again. And so that's the symmetry. The 1 over x is self-symmetric. It is, if you flip it, and you get itself. But here, if you take 1 over x, 1 over x squared, you flip it, you get 1 over squared of x, and vice versa. And therefore, as you flip about the diagonal again, the infinite part that was horizontal becomes vertical, and vice versa, and finite part becomes also finite part. So that's the correspondence here. Okay, so these are some shortcuts that you can take, but basically the definition will solve the problem for you every single time. This is the definition. So just you have to identify whether the integral is improper in the first place, and so there will be some of that that we're going to face. So just for completeness sake, we have to also define the integral to the right when the improper part lies at the right end of the interval. So this one was improper, as you can see. That integral from 0 to b on the left was the missing part. The graph was missing a piece. What if it is on the other side? Well, it's the same exact story. So we have what I'm talking about is now f is defined on interval, say a c, okay, integrable on a b for b between c and a, okay. And then we're talking about the integral, once again, innocent-looking integral, starting from integral from a to c. I'm sorry, this here, excluding c. So it is defined on bounded but not closed interval. So c is missing. So a, c. It might still be defined at c, but what if it isn't? So fx dx, once again, we write out as a limit of regular integrals from a to b. B goes to c minus. Okay, so the b is here somewhere. And b runs towards c. So the whole thing is fully symmetric to the previous one, so there's really no challenge of computations. You take the same two functions as these, and all you do is you just, instead of looking what's happening to the right of the y-axis, you look at what's happening to the left of the y-axis, but otherwise things are entirely identical. So, well, all we just need to do is the definition. So let's just, as an example, I'm not going to do any computations, but let me just write the answer. So for, say, from 1 to 0, 1x dx is still infinite. Okay, so you identify the integral is improper. You go through the computation of the integral with a variable upper limit. That b is a variable here. Okay, and they take the limit, and it is infinite. If I take the integral once again from 0 to, from 1, that's negative 1 over here. Negative 1 to 0 of 1 over x squared, it will be once again infinite. But integral from negative 1 to 0, 1 over square root of x will be not infinite. So sometimes, and that actually will be visible very, very quickly, the actual answer is less important. When you're dealing with, when infinity is expected outcome, just saying that it's not infinity is actually a good outcome, good enough sometimes just to say it's not infinite. So there is a number there. You don't even know what that number is, but at least you know that it is a number. You know, it is even though unspecified, is the idea here. That's what I'm saying here. That's infinite, not infinite. Okay, so it's not infinite, meaning that it is a number. And that's a good news because we can do algebra with numbers, and we don't want to be too casual with algebra with infinities. So with that last number on the right, I could literally do some algebra. For example, I could do Well, so for example, if you take number 1 and number 2, I cannot subtract these two integrals because they are numbers. They are infinitives. However, I could take two integrals like that on the right, and I could do algebra with them. I can subtract. If I subtract from itself, I'll have 0. If I multiply by 2, I make it double. So it is a number. So in calculus 2, it is actually the distinguishing between numbers and not numbers becomes a bigger deal than in calculus 1, especially when we get to sequences and especially series. It will come up, in other words. Okay, so one more definition. It is the integral from, say, C to D, fx dx. Okay, so once again, the integral might be improper on both ends. It's undefined at two endpoints. So then I have limit. I don't do limit. I do the same thing as I did with infinite domain. I split it into two. One will be from C to, say, A, fx dx, and the other one is from A to D, fx dx, for any C in interval AB, CD. Okay, so in other words, we learn how to deal with improper integral, impropriety of the integral at the left end point and the right end point. What do we have both? Nothing. You just split it like this and then deal with each of them separately. You just do what we did last time. So you handle this integral first, and then separately you handle that integral. Okay, and then you add them together. Okay, so it is just a matter of getting used to it, but it's not especially complicated. So once again, before we wrap this up, I want to point out that the things might be much worse than these. These are, even though we ended up with infinitives, it is not the worst thing that can happen. So here's an example of a function that is really poorly behaved. I wonder if you remember what this function is. So it oscillates, and as you approach 0, it oscillates faster and faster. So it's not, yeah?
Sign.
There is a sign there, yes, but a sign oscillates. But how do you make it oscillate faster and faster as you approach 0? What do I put here? I don't put x here. What do I put? 1x. 1x, so when x approaches 0, then 1x is going to infinity, so it will make sine oscillate on and on and on, faster and faster and faster, and that's the behavior that you discover. And not only this function is not continuous at 0, it's certainly also not differentiable, it is also the improper integral does not exist. Okay, so integral, so say from 0 to 1, sine 1x dx does not exist. So as simple as that. I don't say that it is infinite or anything like that, or less than infinity. So infinity is a good outcome. It is informative. This one is, there is nothing we can say about the integral, about the area, even though you can certainly try to, right? So this area, these are the area I'm talking about. So one at a time, you can see what's going on, but you keep adding and subtracting those little areas, and they're just happening so fast that there's no limit. There's no kind of accumulation or pattern of anything. It will not be approaching any number. Okay, so that's the worst case scenario. There you can even think about even a worst case scenario than that if you allow the oscillation to increase in size. So that's also possible. Increase in size as it approaches 0. So it's not only at the end that you will have like a intro like this. That's what this function looks like. At the end, it could be the whole y-axis. Okay, so that's how we handle integrals. And so what has happened is we expanded our understanding of integrals to something that used to be beyond reach. The function when defined at the end intervals. However, now we put these together, and we don't want to really think of them separately necessarily. Why? Because they satisfy the same property. So you might remember some of the properties of Riemann integrals from calculus 1. So let's review those. Well, actually, I missed one more example. Yet another possibility. What if there's a hole in the middle? What do you do? Well, let's see if you can tell me what to do. So what if the graph looks like this? Okay, and I want to integrate from, say, -1 to 1. So once again, if you look at the area, you cannot tell ahead of time whether it's positive or negative, or whether it's infinite or not. So this is the area I'm talking about. Okay, so the function is the same, y equal f of x. Okay, so let's think about it. How do we handle it? How do we figure out this area? We cut it in half, right? So we cut it in half right in the middle. We're not in any place. In the previous example, I could cut anywhere I want because everything was fine between C and D. Here we have to be cutting it at the right spot where the function is undefined, and so that's the origin. So in other words, my integral between -1 and 1 fx dx will be equal to what? Cutting in half, what do I get? What?
0 to 1 of f of x.
0 to 1, right? Plus the other one.
1 to 0.
Right. So -1, 0, 0, 1. So these two are improper, but they have been handled. We know how to handle these, right? So because each of them has only one hole, and so in the end, so that's the missing part is here. So each of them, if you treat them separately, they're fine. So this is one, and this is the other. Okay, so you can handle them separately and just add together. So whenever you see holes in the domain, that's what you do. You cut it in half, and then you continue on with addition. That actually does that what we're looking at. This equation, as well as the one at the top, brings us a certain property of integrals that from calculus 1, property of definite integrals. I wonder if you remember the name of that property, or does it look familiar? Well, let me put it in the form that might look more familiar. So I'm looking at the areas. This is one, and this is the other. Okay, so say this is ABC. Okay, so does it ring a bell? So the purple area, what is the purple area? What is it equal to?
The integral from A to B of f of x dx.
Okay, what about the yellow one?
The integral from B to C of f of x dx.
Okay, so, and now what? We just saw it a minute ago. It is, we were working backwards, right? So here we had one integral, we split it in half, but we could just as well read these equations separately, not separately, but rather in the opposite direction. Hold on, where is it? Where is it? I lost it. That's where we are. No, this one. Okay, so splitting. Where am I? I don't know what happened. Where did I lose my stuff? Oh, here it is. It's just complicated. Yeah, this is the last page. So, the integral we're looking at once again, this one, especially splitting the integral into two it was a plan that we have applied, that idea. But you can read it from right to left, and it is like two integrals are merged into one. Okay, so that is the idea from calculus one, that one that you saw. So if we merge these together, what do we get?
Integral from C to
no, hold on a second.
to
No, from A to C. Fx dx. Okay, so anybody remembers the name of this property? Has something to do with addition, but not summation. So there's the sum rule, you might remember, but that's not what I'm talking about, right? So, how about this one? So that is the third one. Okay, from A to C. Okay, it's called the additivity property. Additivity, which is the not to be confused with sum rule. So in the sum rule, we add functions. So we'll look into that shortly. You add functions, and here you add. What do you add? You add regions as well as you add areas. So you can think of, before you get to the integrals and areas, you look at the regions, and you have two regions, the purple region and the yellow region. You put them together, and you get the green area, green region on the right. Okay, so that's the first level. We are very carefully to do it so that the two regions they don't have too much in common. They in fact have, the only thing that they have in common is this. So they do overlap. Technically, they do overlap. They have this line in common, but it does not affect the integral because why?
Because it's continuous?
No. No, compare the size of this line with the regions. Let me move like this. So what we're talking about here, we put these two regions together, and then we create a new one, and then we're talking about the three numbers. The first representing the first area, then the second area, and the third area. And we're saying that the first area, so area of purple, this area of what is that color, yellow, and area of green. Okay, and then I'm saying that the area of the purple plus the area of the green is equal to the area of purple plus yellow is equal to the green. And then there is that red. You remember you realize that when you take areas and they overlap, there's a plus. Then you cannot just add the two numbers together because the overlap might ruin everything. What I'm talking about. There will be that double counting, right? So if this is 5 and this is 5, this is 10, but this isn't 10, right? Because then there is double counting here. So fortunately, the overlap is very thin. In this particular case, the way we arranged it with integrals, the overlap is very thin. It is nothing but a line, and or what about lines? This line. What do we know about areas of lines? It is 0, right? So the area is 0, so overlap, even though not non-existent, has 0 area, and that's why the double counting is 0. Okay, that's why it works out. So we don't have to look at any extra terms to worry about. So that is the additivity property. All you need to conditions that are required here to be satisfied are the integrability of the function on this integral and then on that interval from A to C, and then you can split it anywhere you want, and you have these three integrals related to each other. Well, the one thing I have to bring up here is the interpretation of the integral in terms of motion. What is it? What is the meaning of, what is the interpretation of integral in terms of motion? What is the interpretation of the derivative in terms of motion?
Wouldn't the integral will be the distance, the total distance traveled?
From, with f being
With f being like what is the acceleration?
velocity.
Okay.
Yeah, so if f is velocity, then the definite integral is the displacement. And certainly you remember that if you backwards early in calculus 1, you should remember that if you have f represents location, then its derivative represents velocity. And now later in calculus 2, you move backwards, and now if you have f of velocity, then its integral will represent your location, or specifically it represents your displacement. So now if we try to interpret this this additivity property in terms of motion, then what are we talking about? A and B and C are moments of time. Okay, so what's the first integral? It is the displacement of you over the time from A to B. And then the displacement of your motion from B to C is the second integral. And the third integral is displacement from a moment of A to a moment of C. So does it make sense then? It makes sense then. You were how far you went during the first hour, and then how far you went, possibly backwards, during the second hour. Taken together, this is how far you went during the whole 2-hour period. Okay, so that's the physics interpretation of the additivity formula. Geometric interpretation is the areas, okay, but always it is a metaphor more than anything else when you go to back to physics, but it helps sometimes because it's so tangible. So now what? No, don't forget that B and C we can integrate. You might remember we can integrate from B to A. It still makes sense. So in other words, when the lower limit is higher than the upper limit. Remember that? So integral from A to B, what's the relation to integral from B to A, from A to B? It's just the negative. Okay, so you reverse time. You reverse time, your displacement becomes negative. So what we have discovered today is that the additivity property is applicable even when the origins, the function might be undefined somewhere in the middle. So that picture once again, this is the additivity property right here. So you have purple here, yellow there. You add them together, understand them separately, and then put them together back to find out what it is. Improper integrals in terms of, now that's a good question. How do we interpret improper integrals in terms of motion? Okay, so once again, f represents the velocity. Okay, so take a look at this picture. The one in the middle. So once again, we know the interpretation. We know that f represents the velocity. Okay, and then the area represents the displacement. Okay, so what are we saying then? What's so special about the velocity in that picture, in the one in the middle? Well, examine what's happening to the function. Starting with -1, the velocity is growing, and then what? Grows. How much does it grow? To infinity. Okay. In the middle, it is in fact at 0. What's the velocity at 0? You can say it's infinite. right? So you're moving it for a moment of time. You're moving with infinite velocity. Okay, so I mean it's extreme. So it sounds extreme, but on the other hand, we just have discovered that it's still possible that your displacement is finite, even though for a moment you're moving infinitely fast. Your displacement is finite. All the examples that we have seen, 1OX, well, let's take this one. So if this is so x is time, 1OX is your velocity, okay? So then at 0, your velocity is infinite. 1OX is a better example. 1OX squared is a better example. 1OX squared that actually produces, not this one, 1OX squared produces a number. Okay, so 1 squared of x, your velocity in the beginning of your journey at that moment was infinite, yet because it was only one moment, it is possible that you will end up with nothing but a finite displacement. Okay, so it's just possible. That's what we discover about it. So there is nothing really prevents us from studying motion when, for a moment of time, you might be moving at infinite velocity. So it's possible. Okay, so that's one property. Since it came up, the sum rule, just to contrast the sum rule with the additivity rule, they really have nothing to do with each other. So the sum rule, what's the sum rule? What's the sum rule of integration? What's the sum rule of differentiation? What's the sum rule of limits? Pretty much all about the same. It's about adding functions. So two functions, you add them together, and then you compare them to the two functions separately. You can speak of limits, you can speak of derivatives, you can speak of antiderivatives, you can speak of definite integrals. So in this particular case, I just want to state the definite integral version. So you split two integrals. You split one integral over the sum into two. As you can see, it is very different from the additivity rule, because we are not doing anything to the interval, to the domain, to the AB. It's the same AB. So in other words, well, okay, we're out of time, but think about what's the motion interpretation of this formula. Okay, so see you tomorrow then.